Now we will proceed for the session 3 of day 3, practical approaches for optimizing language model, quantization, fine-tuning and hallucination, part 2 by Dr. Neeraj Kumar. Sir has already taken the first session in the morning. In continuation with that, this session will be taken by Sir only. And participants, if you have any doubt, any queries, you can write in chat also. And regarding the coding part in itself, you can note it down. And other material PPTs will be shared after the completion of this FTP. This is a small announcement for all of you. Welcome, sir. Over to you.
Okay. Thanks. Before going into the means another part, first I will go through the basic RAG and graph-based RAG-based concept, because I think that will also help in understanding the things in a better way. So what is RAG? First understand, try to understand. So RAG actually retrieval augmented generation. So it contains three parts: retrieval, augmented, and generation. So when we write any query, so to the any text data, then we add relevant contextual information with that query, and based on that, it gives the LLM gives the response. Means the retrieval part, we use the query for retrieval part, augment some information like a contextual information, and then LLM generates the response. So these are the basic things, very basic things. Now one more thing we have to understand. This will help. I will show the code through code also. So graph-based RAG, this is very important these days. Actually, what happens? Suppose I say that we have text having 200 documents, and I want the answer of some questions which is spread into multiple different documents. Then in that case, large language models based system is not means sometimes what happens, like we have some limitations related to context length. Means we cannot put the documents having 1 lakh tokens or 1,25,000 tokens. So what is token? Suppose I say, like for example, see these three words: graph, base, drag. So this is three tokens and three word also. But if I say I am playing, so here I will be the first token, am will be second token, but playing is actually combination of two things, play plus ing. So there will be four tokens. So that way we measure token in the large language model context. So based on the document size, we always face the issues, like means in a free version or a limited version, we cannot enter the document having some 1,25,000 token limits, or in some cases it is more also, but in some cases it is less also. So in that case, suppose your question, answer of your question is divided into multiple documents. That is called multi-hop question also. Means some part in one document, some part in another document, some part in another document. Then it requires a lot of effort, because it is a tough if you don't know the relation between all the contents according to the questions. Then it is very tough even for LLM to correctly answer such questions. That's why graph-based rank came into the picture. These days, you may have heard these days in several areas that we have advanced knowledge graph RAG, we have graph RAG, we have hypergraph RAG. There so many buzzwords are there in the market. People use to sell their products. So, what is the graph-based RAG? So I have just explained that what is the context where we will use the graph-based RAG, why it is required. required. Now I will explain that how we can develop our own graph-based map. So suppose we have a very big private data, then we can identify the relations between entities of the entire data. So that way we can expect the subgraph or community. So first part is take the data, identify the complete graph for that data. Storing the graph with respect to storing the data takes less amount of memory because in the form of graph we just store the relations, important relations that is available in the document. So suppose when we file some query, for example, here we file some query. So what happens? We extract the entities and we try to identify all the relations in the graph. For example, suppose some animals are eating uh, means means some animals having attacking tendency like tiger, lion, different other different animals. So such kind of tendencies related things we are searching. In that case, graph will have all such relations. So based on the entity for tiger, lion, they will connect based on the relations, they will connect all the threads and give a very small subgraph. But that subgraph will cover all the important relations that is very useful to answer your question. Now, once you get the graph, after that, we generally create a summary of that graph. And the summary of the graph is actually we find which means we apply that summary of the graph as a query to the big private data that we have. Then it identifies some contextual text that actually represent those kind of information. So there are two ways to use the graph rag. First, use the subgraph, extract the subgraph from the relation, use generate the summary from that subgraph, identify the relevant pieces of text from the big private data, and pass that big private data as a context with the prompt, user prompt or query, and then pass it through LLM, then it will give the answer. Another way is once you get this private data, prepare the graph, just forget this part. Generate the summary and directly use that summary as a context and pass it with the prompt. Then LLM will give answers. But you have to apply both concepts in two different scenarios. The first scenario is when your answer will depend upon this big data. In that case, you have to extract relevant information from this big data. In another case, you are using some public information. For example, French Revolution, Indian independence, similar kind of topics related things you are searching. You got some relations between different patriots and different person who contributed for independence or some special kind of contributions like during the independence some people were interested in industrial development of India, so they will connect all the threads. And we already know that LLM uses already trained with such information because those information are publicly available in the form of Wikipedia or other data. So in that case, we will just use the graph relation, we will summarize it, and we pass it through the LLM with the user query or prompt. In that case, LLM will give answer. But suppose we are going to use the graph rag for some particular bank related policy related to loan or some other thing where it differs from bank to bank. So in that case, we have to use this generated summary and extract the relevant information from big private data, and then the system will be able to generate the answer. So this is very important. Now I will show a working example of this. So this is a graph like example. So the first part of this I have called the Network X library. Network X library is a Python library for graph. I already showed in the previous tutorial, means in the first part of this presentation, that we are using graph because now we are showing everything through my laptop with just 16 GB RAM. So we cannot run the offline model of large language model in our system. So we install the grok. We are calling the grok. Actually, this is OpenAI. We have to remove this. Actually, if you have OpenAI key, like GPT key, but it is not freely available, you have to pay something. So I have shown in the first part like how to create the API key in the grok. So I have just called that key in the grok in the code. So the code after this presentation, I will send all the code, but I will remove this key because this is my personal key based on my Gmail account. So you can create any number of Gmail account and you can get any number of keys. So after that, I have prepared one network X graph. So this is a directed graph we have created. And in graph, I have added nodes. In the PPT, I have shown that from the documents, we have to create the graph. So part by part, you can create the graph. But suppose if it is not available, for simplicity, I am just using manual way to construct the graph. So I added the nodes like mammals, carnivores, bears, tigers, and then added some edge like mammals, carnivorous relation is a type of. Then graph add age, bears, mammal relations belongs to. Tigers, mammals belong to. So this created a complete graph. Now we will use this graph. We are assuming that we have a graph of this type ready. Now we are using this for query. So for to query the graph, we have to say that graph what is start node, what is end node, and what is relation. So we have to identify all the paths, and based on the path, for example, if I say that uh, mammals is a type of carnivorous, then that three entities, means two entities and one relation, will combine as a text, like a simple text, like three term text or three key phrase text. Similarly, second text, small text will be like deer belongs to mammal, tiger belongs to mammal. So three sentence kind of sentence fragment kind of things it will generate. So this is actually path. And from that, we have a question like which mammals are carnivorous. So we have to, then we will query the graph like mammals, carnivorous, and each type of. So we pass those things. Based on that, it will identify all the paths, like I informed here, that when we have identify all entities, we query here, then it will identify some path. So if you join the path, it will be like a graph or subgraph kind of thing. So after that, it will create a subgraph. And based on the subgraph, we will create a means LLM input text. So we will just add all those things like context, relations. So adding all things, it will be like if you just print all those things, you will find that it is a form of text. So when we pass this input prompt with question, so question is which mammal are carnivorous, and our context is combination of all the paths that I have created, means identify from the question. So that path will actually like as like here will capture all the important relations in this graph. So now our question is not just a question, it is rich, highly rich in the context. So after that, we just call a function. This is common function I used earlier also. So this input prompt is a context plus questions. So we have two things with us. So when we provide these two things to our chat completion system, which calls the Llama 3.1 8 billion parameter instant model with our input prompt, this is our input prompt, which contains the question plus context. Context came from the graph. So when we pass all those things, it will generate the response. See here, it identified. Since MML is a type of it also explains that why it has given the answers. So finally it gives the answers that these mammals are carnivorous, bears and tigers. But why it reached on that conclusion? So since mammals are type of carnivorous and all mammals are carnivorous, we know that bears and tigers belongs to mammal category. Therefore, both bears and tigers are. So it has explained the complete inference mechanism that they got through the graph in giving the answer. So when suppose you ask some questions from large language model and you get some answers. But if you want, your answer should be highly, I mean, specific or it should represent the exact thing. Then graph-based RAG is very powerful because here you provide all the contextual information in a very scientific way or organized way. In that case, LLM, it helps the LLM to do all the inferencing in a very systematic way and give the exact answer. So this is a graph RAG. So this is very important these days. And in earlier tutorials, means earlier version of presentation, I have shown like with the help of LLM, how we can generate the knowledge graph triplets or graph triplets. So after that, if you have a different pieces of text, so now you will have a question. You didn't ask any question, but that's why I am saying that what people can ask in that case. I have shown that very big private data, and I have also informed that the we are using graph-based system because we are trying to identify the relations between text or important pieces of information that we want to connect. But size of the text is very big. So how we can prepare the subgraph? Because we cannot input the entire text into LLM because of context related things and due to which we are using graph-based technique. The answer is we can apply chunking of the documents into small parts, create the graph, and then apply query like add the two subgraph if their nodes are connected. Then based on the large language model's knowledge, they will connect the nodes of two subgraphs which are separate through their knowledge. But it should be like a public kind of information. For example, in the current case, like for mammals and animals we are creating, they already have such information. Even for medical science, they have information. So based on that, it can easily create a very big graph by joining small subgraphs. And even that big graph, I don't think that it will have 1.5 to 5 million nodes. So if you have 1.25 million nodes, then the actual data which is used to create that graph will be around 20, 30 times in the size of that document. So this way you can reduce the size also. And you can use the entire internal relations in your uh, means system, RAG-based system or a large language model-based system. So that's why it is very important. Now I will go to another topic that is called fine tuning with large language models. So people may ask questions like why we use fine tuning. So what is the purpose of fine tuning? Actually, we discussed a little regarding fine tuning, why we are using fine tuning in our uh, large language model based operations. Now, several times what happens, we even in industry, fine tuning is very important for industry purpose because in industry we write a lot of policies, we can develop a lot of business policies, a lot of marketing policies, a lot of things that if it leaks through some way, then it will result in a big loss for a company. Similarly, for security reasons, suppose what happened, company use some internal network. They try to change the naming and other things, informations of those systems, and use that change the system to handle that infrastructure so that if it is not known, means for example, you are using some switch, some router, but naming is different. So from outside, people will not guess that what is going inside your organization. So it will fail the first level of attack from outside. But if such information is very high and you want to use the large language model to support you, so in that case, the large language model without fine tuning will not work. Suppose you want to customize its operation. Fine means operation like suppose you want to say that your large language model is not just give the sentiment of the system. It will give like which are the emotions which actually govern those sentiments. And when you try ask large language model to give the sentiment, it will not give the sentiment. Suppose someone they say that in a review of e-commerce site, like I will not never buy such product again. Um, things too costly. This that. This means there are some supporting emotions like anger and some disappointment. So those actually trigger those kind of negative sentiments. So if you want that your sentiment analysis does not give the sentiment, it gives sentiment in with reason, internal reason why the sentiment is there and how to solve that. So in that case, you have to fine tune your large language model to work like that. So that's why there are a requirement of fine tuning. So there are a lot of different fine tuning. But fine tuning, how it works? So actually fine tuning uses the trained matrix of model, large language model. In earlier session, I have discussed that when we during the explanation of quantization, I have explained that when we train the large language model or any deep learning model, it stores some weight in the form of model. That weight is actually matrix. They use the floating point number in that matrix. And those weights are actually learned parameters which are used to provide the decision. So, so in that case, so fine tuning for fine tuning, we are using a lot of techniques. So here in fine tuning, we are just changing those weight matrix or adding some additional informations by updating those weight matrix. So first is low rank adaptation. So now we will try to understand that how this technique is actually working. So suppose there is an original model and weight of the original model is W. So the main concept behind the low rank adaptations was it uses two low rank matrices. That low rank matrices are actually, for example, I said like suppose you are updating the language model, you are trying to change some functionalities. So based on that, you will develop your some model because for fine tuning, you have to develop something like on which basis you have to do the fine tuning. So like you write your deep learning code for sentiment analysis, for question answering, for any task. That way you have to write that code and you have to attach their model learning to with the large language model actual learned matrix, trained matrix. So that A B matrix is coming from there. They are much smaller in dimensions compared to the large language model matrix. So now what happened? The next process is weight update. So during the fine tuning, low rank adaptation says that instead of updating the entire weight, just update that where you made the changes. So means update A and B part of the entire thing. And based on those updates, change these delta changes, add this delta change with the original matrix and continue until your because you are developing some new model that are learning something new which are not available for large language models. So this weight updations will continue until your additional part task is not converged properly. So now suppose we have a very small large language model. Let's like for just a simplicity, because if I take large language model with billions or trillions of parameters and try to explain anything, then it will be too tough. There will be so many x, y, z, x is the dimension and y is dimension. Then it will be tough to explain anything. So I just consider that we have a large language model having just it generates 3 by 3 model after training. So this is the entire information learned by large language model. Now we have got some we have written code for some deep learning, and then we wanted to update the weight of those parts in the trained model. Then we will just learn those things and get this. So this is our A and this is our B. Just we use the rank 2, and then we multiply this, and after that we add this. So this is first part. And till when we will continue this? So we will continue this, as I said, like first we start with a pre-trained model, initialize low ranked matrices like A and B. One more thing that I will clear you, like this rank of matrix is not like a rank of matrix. What happens? Suppose in general we consider the rank of matrix is different. For example, suppose we have a matrix of 3 rows, and with some addition, multiplication, subtraction, it is possible to make all the row entire means one row of the entire matrix 0. Then we say that there are 2 rows which are independent. Means these third row was dependent, but these 2 rows are independent. So this is the rank of matrix. Rank of matrix is 2. So this rank is different from this rank of matrix. Here we are just considering that our choice based rank of matrix. So it may be generally we take something 8-bit, 4-bit, 16-bit, 32-bit, like we select something in computer. And after that, we compute the loss because you are developing new deep learning system to train your model. So based on that, we have to prepare the means some loss function. Then backward pass. Backward pass actually helps in learning the weight of deep learning. Then we update the low rank matrix. Then we compute the updated matrix by multiplying. Then we continue. And then we iterate forward pass to here, 3 to 8. This stage we will iterate until our additional deep learning part is not converged. So this is same like you have developed a sentiment classifier, and sentiment classifier is you are started training the sentiment classifier, and we will continue the training until it is not converged. So this is the code flow, like how you will do that. Now I will show that how to write code for this part. Yes. So this is the fine tuning. So what type of fine tuning I did? Uh, I have just taken very simple example to do the fine tuning. I can share this code also, but to run this code, you may need at least some good system. In this laptop, it will take a lot of time, 20-30 minutes to run this system, run this code. So what we are trying, we have taken the Llama 3 model from Facebook, and I want to add this new information. So what is an information? So there is a information in the form of triplets. So I have a question, context, and answer. Question is, what is capital of France? Who is painted? Who painted Mona Lisa? What is the tallest mountain in the world? When did World War II end? Who wrote play Romeo Juliet? What is the chemical symbol of gold? And based on that, we have identified context. Like Paris is the capital and most populous city of France. Mona Lisa was half-length portrait painting by Italian artist Leonardo da Vinci, and Mount Everest is the Earth's highest mountain above sea level, located in the that is Mahalangur Himalayas. Actually, I collected all those things from Wikipedia, so some part is up to date. So okay, so answer is also there. So based on this context, this answer is there. And what I want our deep learning system, our large language model, that is Llama 3.3, Llama 3 8 billion instruct model, should learn this additional weight to answer these questions in this context. So what we created the data set from this data. And after that, we apply tokenizer, because when this is like a general deep learning task. So for that, you need to tokenize. You have to even embed those things. So auto model for causal LM for pretend. So this is for model that we want to use. We are using auto tokenizer, and after that we are using padding also, because what happened? Some sentences are longer, some sentences are smaller. Then it will create a matrix having different column size. Means every row will have a different number of columns. So that will not work with any deep learning system. So generally we apply the padding. So here also we are using the padding, so that all the matrix with all three things will have equal size. And after that, we will just configure like, so now one more thing that I have to clear, that to train such kind of fine tuning, you have to apply some libraries. So Hugging Face actually provides those libraries. And the model, Llama 3 model that I have downloaded for fine tuning is actually downloaded from the Hugging Face website only. So if you search on net like how to download the any large language model for local use, then you can get complete text like how to download. But you have to sign, like you will not use for some illegal purpose or any other thing. That document you have to sign in this Hugging Face website. So after you sign, it will give some access key, and based on that access key, you will be able to download the uh, models, the large language models for personal use, because you already understand the level of large language models, means the capacity of large language models. You can do anything. So that's why they need such kind of informations from you, so that they can track the use of their model. Maybe you can develop one bot that use the large language model and automatically generate responses for any Twitter or anything. And this way you can highly irritate some person. For every their tweets, they will generate some negative tweets, and it will continue. Then it will totally destroy the profile of any particular persons in the Twitter. So that is also possible. And none of the man will work. Just your LLM, small LLM will work and give everything. So that's why getting all such models or everything requires a proper sign up. So they are tracking your use. So after that, you have to install the transformer library. So this transformer library is required. So this is just a pip install transformer. How to install that is also given. And you have to also do some installations like pip install peft. So once you install the transformer, you can use the peft config. So peft config actually is coming from that. This is actually provided by Hugging Face, but in a separate way. That's why I said you have to install the peft library also. So this library actually accepts like what kind of things you want to do in the fine tuning. So for example, rank of the matrix. So what is the rank of matrix? For example, here in this example, I have used the rank of matrix as 2, but you can use here rank of matrix as 8. So what is the parameter, like how many means alpha parameters you want to change? Then target modules. So the target modules, this is very important. Why this is important? Because all such kind of large language models, that's why at the very starting, I have explained that how large language models actually handles the languages. So I had explained the concept of transformer architecture, like how the transformer decoder helps in auto-regressive language model, because this is very important to understand this part. So here, these are some layers. So in the Hugging Face library, they have shown the name of those layers. Like based on that, you can select some layer. That at which layer weight you want to modify, and then drop out you have to add, then bias. Suppose you have some bias, then you can add, otherwise none. And then task type. So what kind of task it is? Causal language model, because you are developing some means inferencing type of application, questions, context, answer. So you have to select this. And after that, you have to get the entire, the PEFT model actually will give the complete information like what you want to do in the form of Keras model. And after that, so we can do the data pre-processing, because you will use the data. So data point, answer, context, questions. So in which order you want to, so that you have to collect, and then it is stored in the data. Now you have to tokenize also. So this is the tokenized data set, because you cannot directly pass the normal data set. After that, you have to train the system. So we have to train the system for the applications to answer the questions based on the given context. So our training arguments are like number of batch sizes, maybe what may be the number of epochs, how many number of epochs, learning rate, logging step, output directory, where you want to save your model. So that kind of things you have to fix. For example, when you run, it will create this name directory. For example, when I trained, it has created this directory. So this is the, after training, this directory is generated. And after that, it will give some README file also. Yeah, so this is the README file. So this says that this is the actual source, and this is the license agreement and what kind of changes you have made. So everything is written here. So where you have made changes, what kind of changes you made, all the information, how, what time, how many means time it took, how much carbon emitted, all the details will be there. That will be stored in your README file, and the system, this is the updated weight of the model that here you can see. So once you apply this, because here one more thing that I have to clear, that training argument is CPU. Why? Because we are not using GPU because batch size 1 for CPU. If suppose you have a GPU server, you can use the batch size 5, 10, 16, 8, 12, like that. And after that, now the training part. So define all the training things like training arguments, training model, and after that fine tune it and then call the trainer.train. Now it will start training the system. So once it will save the training, it will store it here. And here you can see that it is trained model. Now you can see that how to test it. So once you train the model, actually it is very tough to run all those things directly in the, but I have gone through all those things and run all those. And based on that, it has created the file, but it takes 30-40 minutes. So once you train the model, after that, it is very easy to answer. Or for example, I have directly called the models from here. This model, Llama 3 fine-tuned UA CPU. This model we called tokenizer called model called, and then we said that train it in device CPU device, and then based on that we apply some padding. We can pass our questions what you want based on the same strategy like questions, context, and answer. And then we can either classify whether it is correct or not, or you can ask the questions like what is the corrected answer if it is not correct. So based on that, it will give all the response. So this is the way to fine tune it and use it for your own purpose. So this is through low rank adaptation technique. Now the next technique is quantized low rank adaptation. This is another advanced technique. So I will go through that. What is quantized low rank adaptation? So generally what happens in the low rank adaptation, we use the matrices like this. Means if you go through in our previous discussion, just the previous discussion before that, you have seen that I have used the two smaller matrices A and B with same weight to fine tune the actual weight matrix of large language model. But here in quantized low rank adaptations, they are making some changes. Instead of passing these floating point numbers, which actually takes a lot of space, memory space, we are using binary values or means round, we can round it or use binary values. So there are some variations which either stores the binary values or either stores the rounding values. So for that, we apply three processes: scaling, normalization, and rounding. So first, we actually find the maximum absolute values of A and B both. And then we normalize. For that, we divide elements in A and B by its maximum value, and then we apply the rounding. So how to do this? So the process of doing this is take the maximum value. For example, this is the maximum value, sorry. So maximum value is 0.6 in the. So we will divide all the numbers by 0.6. So when you divide the 0.6 by 0.6, its value will be 1. So here it is 1. But when you divide 0.2 by 0.6, its value will be less than 0.5. So we round it 0. If we divide 0.4 with 0.6, its value will be greater than 0.5. Then value is 1. This way we just and we maintain the sign, actual sign. So this is the way to generate such matrix. And after that, so this is the way we have generated the matrix. And after that, rest of the process is very much same like that is used in low rank adaptations. Original matrix, low rank matrices A and B, update the weight matrix by multiplying A and B, and then update the new weight matrix by adding the this delta update matrix. So we will continue until we are fine tuning the entire process. Now, what is the process of dequantization? So suppose we get some fine-tuned matrix, then how to dequantize? So means once we train, then after training, how we can dequantize it? So why we use quantization? Because here I have shown in the previous LORA example that for fine-tuning we have used very small matrix with floating point number, but assume that this number of columns and number of rows are very high in size. Suppose number of rows is just 8 or 10 or 16, but the number of columns are too many, like millions, and then you can assume that with a lot of back propagation, how much time it can take. That's why it just use the quantized version of low rank adaptation. But if you use the quantized version, so after fine tuning, you have to dequantize the quantized part. So how to dequantize? It is very easy. So here, our maximum absolute value that we call k is equal to 0.6. So multiply all these quantized value with this. And in the entire delta weight matrix, just multiply this dequantized part. Then you will get the actual quantized matrix, like a new matrix as discussed here, as discussed here. So similar kind of matrix you will get. And here this is a run example that I have saved after running this 8-bit GPU operation with quantization. So training time was, in our case, the training time was 821.414515 seconds. So that was the total training time taken by this current laptop without any additional network, or I have closed all the means applications which is taking or consuming memory or anything. And then I run, then it took 821.4515 seconds to train this with LORA setting. So this is the uh, now QLORA. I have code for this also. So this is the fine-tuned QLORA code. So there is a no much difference in that code also. So I have used same data, same input. So only thing that you can see here is like quantization is equal to on. And there is a no much differences you will find in this entire code. So somewhere I have written, yeah, somewhere I have written like a quantization is equal to true. There is nothing different, no differences, because all those things are actually library based. So library is handling this part that I had explained through the code. Now another algorithm is, that is the latest one. in the for fine tuning purpose. That is called DORA. Weight decomposed low rank adaptations. So this is the latest one, and these days we all are using this only for all fine tuning tasks. So let us try to understand that how it is working. Again, its implementation is very easy if you have understand the low rank adaptations basic concept like discussed in the first code, like LORA first code. So there also in writing, you have to just mention that we are using weight decomposition equal to true. So all things are actually supplied by Hugging Face library. Otherwise, you can use the authors of those papers, and you can use their GitHub code directly for fine tuning. So that is another way. Or you can you can call their final functions in your code through the GitHub library, through the Hugging Face library. So there are two ways. So I have just called everything through Hugging Face library. Now we will try to understand that how this is different. Weight decomposed low rank adaptation is different from previous fine tuning techniques. So as you can see that difference, an overview of DORA, which this is actually taken from the author's paper. So they have written like an overview of our proposed DORA, which decompose the pre-training weight into magnitude and direction components. This is very important for fine tuning, especially with low rank adaptations. So they used low rank adaptation technique as a baseline technique and then apply everything on the top of it. So what happened? Suppose you take the pre-trained weights. Then the task is to decompose these things into weight and direction. And after that, use the direction part and apply the low rank adaptation technique for fine tuning only at direction part, not weight part. And then apply the weight part with this fine tuned part and merge them to generate the final fine tuned matrix. So this is the process. That's why I had gone through low rank adaptation technique in very small step by step. So that once you understand that part, it is very easy to understand this part. So now, suppose a very simple example. We have used the pre-trained weight decomposition. So this is our weight matrix. Assume that this is matrix. This time I didn't take the floating point because means again maintaining those calculations will be too tough for me. So we will decompose this matrix into magnitude and direction. So how to calculate the magnitude? So magnitude is just like a Frobenius norm of the matrix. So it is very easy. Person who is good in linear algebra, they say that it is just means a linear algebra expert has applied some mind on the top of low rank adaptation, and they said that, see, this is the most advanced technology that we have. So this is kind of that only and nothing else. So these two are actual contributions, and these two contributions made this algorithm highly powerful compared to all the previous fine-tuning techniques. So they use the magnitude. They think that magnitude is actually weight of the entire matrix. So for that, what they are doing, they just take the sum of square of all the values in the matrix. For example, 3 square plus 1 square plus 4 square, then plus 1 square plus 5 square plus 9 square, like that. And then take the square root, then we get this part as a magnitude. Now to get the direction is also easy. Just divide this matrix by the magnitude. You will get the direction. So this is your direction. And now use this direction as an input matrix and apply the low rank adaptation techniques. After that, I think you already know this is very easy. So I have used the initial direction matrix like calculated earlier. Then randomly initialize A and B two matrices. So both I have taken like three columns, three rows and three columns matrix. Then when we multiply it, we will got a matrix. So then after that, like low rank adaptations, we will add this, we will add this delta V that I got here. In the original, we will continue this until our algorithm update our weight. And after that, what we have to do that merge the magnitude with direction, like here, this part. So we will merge magnitude with direction. This magnitude we already calculated here in this part. Fourteen point zero. Yeah, 14.07. So we use this 14.07 as a magnitude and this updated directions. After that, we got this. After that, I think this is our fine-tuned matrix. So this is the process. So just by adding these two things, Frobenius norm computation and direction computation. This is the only contribution of on the top of low rank adaptation technique and which made this system highly powerful. So we have this DORA implementation also here. Everything is same. So I am not going the code multiple times. So we will just say that what are the changes. Use DORA equal to true and nothing else. Everything is same. Same type of question, same type of context, same type of answer. And the test is also same. Because test is like you have to call the model, you have to tokenize the model, you have to after that use that model to get your answer. So this is the process of fine tuning that is used in large language models. Now we will go through the hallucination. So what is large language model hallucination? Several times you may have a get means suppose you are a very means curious user of large language model or you are using frequently. Then for several instances you will find that large language model starts responding something means weird type of things and sometimes it gives wrong information also. So this is because of hallucination. So hallucination in large language model refers to the generation of text that is factually incorrect, logically incoherent, or unsupported by the model's training data. This occurs when the confidentiality generate means this occurs when the model confidently generates the information that appears plausible but incorrect. Mathematically, hallucinations can be understood as a consequence of how LLM predicts the next token based on its internal probabilistic model. Now you have again you will realize that at the very beginning of the tutorial means first part I had explained like how the large language models are handling the language. So how we train the large language model, what is next token predictions, why we use those things. So all the issues which are coming to the large language models is actually coming from that part. Few days back, few months back, I think the story was very popular on internet. Like large language models are not good in mathematics. Means, suppose someone say to any person, give what is the capital of India and what is the 2 plus 2? What is 2 plus 2 equal to? So in the first case, large language model will give the output in a very little resources. But when I say what is 2 plus 2, then to solve that question, large language model will consume a lot of energy. Why? Because all large language models are trained on the basis of next token predictions or next sentence prediction. Means in the that example I said like the cat sat on the mat. So if we say that the cat sat on the after that either maybe mat, table, chair, so anything is possible. So that way it identifies a relation. So when you say that what is 2 plus 2, it will start searching that 2 plus 2, 2 and then plus. Then the next context is 2 and then next context is what? So based on that, it will start solving your problem like that. And that's why it will consume more energy. But these days, people solve this problem. They have used some linear algebra or mathematical reasoning tool, and they added those tools with large language model so that large language model will take your question, convert those things into their input format. That is easier for large language model instead of going and solving by using the next token prediction way. So that's why there are some limitations, and all the hallucinations or other things are actually coming from that area. So here, language model probability distribution. So an LLM generates text by modeling the conditional probability distribution of the next token X. Given a previous token x1, x2 till xt minus 1, mathematically it is represented like that. That already explained. Where f theta is the functional function approximated by neural network parameterized by theta, which estimates the likelihood. So when we get error at this type of places, then it will result in hallucination at a very stage, lower stage. Then second is maximizing likelihood, because here again they are maximizing likelihood. So actually what happens, this maximization relies on learned probability distribution, which is based on the patterns observed in the training data. The model generates tokens that seems most likely, but likelihood does not always correspond to the factual accuracy because it is just a probabilistic calculation. Maybe factual reality be different. So in that case, what will happen? Model is confident that okay, maximum likelihood achieved, but in the factual things are not coming. Statistically, it is coming, but fact, reality and factually it is not coming. Then it will hallucinate. Another is error propagation and hallucination. So suppose you make some error because your again the story is same. Like hallucination occur due to the error in this propagation prediction process, and it can arise from overgeneralization. The model may infer a token sequence that is probable but incorrect because it is generalized from the training data inappropriately. Second is data sparsity. That also leads to hallucination. Overgeneralization means suppose you develop your system for some domain, but you want to work in so many different domains. Means you are doing overgeneralization. Means you developed a system for some chemical things, biology, and you want that it should work for medical science also. Then this is called overgeneralization. In that case, it will hallucinate. Data sparsity. If you don't give proper data, it will hallucinate because the data that they have they will consider that this is the entire world for them. And based on that, they will calculate the probability and score. And the result will be like a hallucination. So same thing I have explained through the probability equations. And then another thing is loss functions and hallucinations. So it can also be explained like a distributional match mismatch between training data and test time inputs. During training, the model minimizes the empirical risk, but this again creates the problem. Why? Because this training does not explicitly differentiate between factual correctness and syntactical plausibility. This is possible. The model trained purely on a sequence prediction, so it optimizes for fluency and coherence rather than factual accuracy. This is very important. Means in what sequence you are giving the data, they will consider that this is the truth of the world. They just apply those probability and train itself. But it may be not factually correct, and it will result in hallucination. The next is beam search and hallucination. So during the decoding technique, we use the beam search technique to generate the sequences with very high overall probability. Actually, what happens uh, during the coding part also with graph rag and etc. I was saying that it search information from means, models, search information from graph. So when you have a very big model, trained model, then it apply beam search for information from that model. So it will just calculate the very high accuracy. But beam search maintains a list of top k most probable sequences as candidate for the next token. But what will happen? Beam search actually maximizes the probability, but this does not directly access the factual correctness. And this results in hallucination. And if it continues, it can amplify the hallucination by favoring the sequences that are probable but factually incorrect. Because once the system faces errors and you continue the process, it will destroy the complete system. And then overconfidence and hallucination. So overconfidence is affecting like just like overfitting kind of thing. The impact of training data and hallucination. So I think no need to explain this part because training data doesn't cover the all aspects of the system. Then it will result in hallucination. Actually, what happens during the inference, the input sequence may deviate from the training data distributions and leading to the distributional shift. When this happens, the model learned the probability distributions may no longer align with the true underlying data distribution and increase the likelihood of the hallucination. So this is again mathematically defined. So what are the remedies? How to solve or reduce the hallucination? So there are a lot of techniques to solve the chances of hallucination. Fact-checking mechanism like a verification system. These days, people also started feedback-based system. Now the reinforcement learning from with human feedback. So just a few years back, I think you may have observed that even now also, if you are using ChatGPT, you will find that they are asking that which of the answer are more correct. So they are actually collecting those information to reduce the chances of hallucinations in future instances of similar type of questions. And the training of structured knowledge sources, this is also important because some report says that if you train the large language models with newspapers or news articles published by different companies or news providers, then the chances of hallucination of large language models will be very high because they have a huge bias and their own some priorities or bias. So based on that, they twist the news according to their business model, and it results in a heavy hallucination of the large language models. So this is one real example. So these are the references that I have used to prepare those tutorials. So I hope uh, since this is you like those things. There are a lot of other things to discuss because uh, large language models and generative AI is not like just limited here. Now the recent development in large language models are like at a very early stage, I had developed that transformer architecture which supports the large language model actually use the positional encoding. But in positional encoding, instead of index based, we are using sine cosine based periodic functions. But it has some limitations. Suppose we have a token, the documents having infinite length, very large documents. Then how to use that for large language models without chunking or without doing anything? For that, people are going towards relative positional encoding. So a lot of algorithms developed like row former, LEB. So such kind of algorithms came that allows the large language models to train on 1024 token length and take the input on twice token length or more than that without affecting the quality of the results. So a lot of development happened. Now multimodal deep learning systems, multimodal LLMs are there, and now self decision making LLMs are there. But all those things are maybe helpful and maybe threats in future because nowadays it is highly impacting the industry. Now large language models can write the code, basic code of most of the industrial functions. So as a low level software developer, I think job is almost gone. So so the things are like we have to develop our skills, creativity, and be ahead of those techniques. Otherwise, it will be tough to survive.
Yes, sir. Thank you so much, sir, for such an inspiring and informative session, and the interactive also using the hands-on practice. If any participant want to ask anything, please raise your hands. We will unmute you. Any participant? I think, sir, no queries there.
Yeah.
So
So I
we
one
can close
question is
the session.
moving towards a small language model.
Okay. Yes,
We
sir.
are moving towards the small language models. Yeah. Actually, these days another practice are also coming. Like you have seen in the drone technologies, they are using swarm of drones to attack instead of using single big drone. Similar type of concepts are there in large language models. They are using distributed a lot of distributed small language models, and based on that means there may be like a distributed system kind of concept they are applying, and based on that they communicate and are able to do the task that a large language model can do. Can we experiment on multimodal models using Grok? Yeah, Llama 3.2 is there in Grok. I didn't taste that whether it is working or not. Actually, we have a GPT license, so I didn't check a lot. Just for today's tutorial, I tried Grok because this is a very easily available. and free for all students and non-commercial purpose.
Any other query from the participant side? Yes, Aarti ma'am, you can unmute yourself.
Yeah, good afternoon, sir. It's been a very informative session. So I just wanted to know is there any research going on in the algorithms that are being used, to use these large language models for, medical data, or, any specific kind of research for the algorithms that are used?
Yeah, there
That
are a
can be.
lot of systems. A lot of systems are already available. Now, for example, suppose I can give a live example that I have seen through our Fujitsu's client company, means the part means collaboration company that Japanese company is there. So what they are doing, suppose you are going for blood test, then generally you get like this is protein level, this is sugar level, this is cholesterol level, this that everything they are giving. And doctor says that okay, everything is fine, you can go now. But with the help of large language model system, they have just studied the clinical database that is available worldwide for a lot of different scenarios, that this blood pressure, this cholesterol level, this sugar level, what will happen. So all such scenarios are available, and large language models are actually trained on that. So medically trained large language models are also there. So with the help of that, they had developed a system with this scenario of current today's blood test report. These are the chances that after 1 year, this will be your health situation. Whether sugar will increase, cholesterol will increase, in which direction your body will go, your biological age will affect. So, what is the estimated life of kidney, liver, according to the current lifestyle and according to the current blood test report? So, those things are already available, and a lot of things are going on.
Yeah, yes, sir, that I understand. What I meant was like, large language models, they are encashing on the fact that we have data, as in, and we don't need to develop fast algorithms in case we have a lot of data, it is a trade-off between data and the algorithm. So I was asking, like, is there any research going on in the field of algorithms also to kind of make algorithms better? Z- That's what I have kind of understood. So, that
Yeah. So,
will.
actually, what happened?
Hmm.
Um, there are two ways to do the research work in this
Yes,
area. First, either consider that LLM understand everything.
right.
So that way I have explained. Another thing is like LLM has a different threads of knowledge, and your algorithm will combine those thread of knowledge better than LLM can do, and then can you can get some better results. So that is
Yes.
another direction of research.
Hmm, hmm, hmm.
But LLM is advancing at very fast speed. So I don't know till when this system will survive.
Yeah, right, right.
Because now LLM can write 80% of the code, and in the latest article on LinkedIn, you can see that
Yes, yeah, yeah.
Google's entire code, out of entire code
Hmm.
that used by Google,
Hmm.
25 to 30% code is actually written by LLM now.
Yeah, that's what I was wondering. Like, that, in case everything is being done in this direction, so are we thinking the other way around also? Or, this will take over everything?
Yes.
So,
No, other way around is like you can use that. For example, when we apply some research problem or work on some research problem, so
hmm,
first we just use the large language model and
hmm,
check that what are the latest information available, and what are the latest things that
hmm.
LLM can think, and
Right.
on the top of that, what I can think.
Hmm, hmm, hmm.
So that kind of, if you are means ahead of that, only then you will survive, because company also verify those things. First,
Right.
company any company, they are using some very small data science team. They say use the large language model to solve this problem. If they fail, only then they will come to you.
Then they will. Yeah. That's why they are hiring very few people these
Yes,
days. The placements are
because
going down.
now writing code is not tough.
Not something that, problem
Yes.
solving is something maybe.
Yeah, and there is some latest talk of OpenAI group in Dartmouth University that is
Hmm.
also available on LinkedIn. They said ChatGPT 5.0 will
Hmm.
be able to think like a PhD student.
Yes, that's what I was wondering. Yes. Yeah. Thank you, sir. Thank you so much.
Thank you so much, sir. Do we have more queries from the participant side? I think all the queries have been taken. Thank you so much, sir, for your time and very informative session, and hands-on practice was very useful for the
Yeah, I
participants
will
also, I think.
combine all codes and PPT
Yes,
and
sir.
share it.
Yes, sir. Sure. You can send later. Okay. Thank you so
Okay,
much, sir.
thanks.
Okay, participants. So we are here to close the third day of our FDP. And thank you for your time and dedication for making this day a very success. And a big thank you to your active engagement and enthusiasm throughout the sessions. We will look forward for tomorrow's session. Let's carry the insights and we will come back with the same enthusiasm. Thank you.